Let's get started with day 2 of the workshop on scalable statistical inference. And first speaker this morning is Michael Jordan from Berkeley.
All right, it's a pleasure to be back here. I've been here several times. Had a memory, a flash. The first time it was a conference organized by Mike Titterington. I think it was the first or second year the institute had opened. And I just remember in that room over there was a crowd of people studying algebraic topology or something. They were all Russians, and the whole conference was in Russian because the Russian diaspora had just started. The USSR had crashed, and Russian mathematicians had been spread over the entire world. So they came here, and they ran their own little conference, heatedly debating each other in Russian. Okay, so I'm going to talk about optimization today. So I thought I might start with excuses about how optimization relates to statistics and all that. It's not particularly Bayesian and so on, but I'm not going to do that. You all know that optimization relates to statistics, and I hope you've kind of followed the last 20 years that fundamental progress in optimization has really been very important for our field. And going forward, it's going to be more important to talk about scalable things that are scalable in number of data points, but also in dimensions. We really have to get the optimization right, and we don't just borrow old ideas from optimization. And I'm also going to argue that any field that's sufficiently mature starts to use the fundamental theorem of calculus. So it starts to look at the interplay between differentiation and integration. And so the deepest fields are ones that have really explored both sides of that interplay. So, obviously physics, there was Newton's laws, which were differential equations. So talking about vector flows, vector fields, derivatives, and Lagrange came along and said, well, you can reformulate all that in terms of integrals and optimization. So he reformulated it as an integral that you optimize. And that, of course, interplay has been extremely productive and deep in physics. In fact, the integral approach eventually sort of took over, but they're both present all the time. And we see that in ideas borrowed from physics, like Laplace approximation. We saw a talk on that yesterday, where you take derivatives to do statistical inference that approximates an integral, and then more generally in saddle point expansions. And if you look at the numerical disciplines, the most mature parts of them also have this interplay. So finite element analysis is a variational methodology for talking about partial differential equations. So you write down a PDE, and then you turn into a variational problem that is an integral that you optimize, and that's been for now many years the state of the art. And then in Monte Carlo, you have various methods that are trying to integrate, but they blend in derivatives in important ways. Now, the field of optimization itself is a venerable field, but it's probably not as old, and I don't think as mature as these other disciplines. So, in fact, if you read papers in optimization, you will not find integral signs almost anywhere. And you will not find variational perspectives that much. You'll find them, but in a more of a convex analysis sense. So you'll find them as in a Taylor expansion, the remainder term, and that's sort of it. So I'm going to argue today that there's a closer relationship within the field of optimization to integration than people have perceived so far. It requires going into continuous time. And so that's kind of a new thing for that field. Almost all the work in optimization is about discrete time, and it's about control over how much you can move as you make hops around the space. So Lipschitz constants and strong convexity constants and so on are just control the amount you can move, and there you put that all together usually in some kind of a telescoping sum, and that's how the proofs go. So we're going to do something in continuous time, and it'll be a little different. One more word about optimization. So I learned it, I think, in the 1980s. And it was viewed as a mature but also dead field. That the best methods were known. There was conjugate gradient. There was BFGS. There was constrained versions. There was non-constrained. There were infinite-dimensional versions, and so on and so forth. And rates for all these things were known, and they were favorable rates, and people were using these ideas in practice. So what could be better than all of that? And as soon as a field kind of looks like it's done, then something revolutionary happens. And so there was already a little hint of that with interior point methods that sort of shook people up a little bit. But then this line of work that came out of Russia, in fact, that's kind of why I alluded to Russia earlier, Nemirovsky, Nesterov, Polyak, and others really completely changed the field. And the last 40 years has been mostly that perspective. And that's the one that's been most relevant to us. So the basic key idea was Nemirovsky's, which was that there's a way to talk about a complexity theory of optimization. That there's not just a way to optimize a particular problem, but there's a best way. So there's a lower bound. And again, fields that are mature have lower bounds. So statistics has a number of lower bounds that are meaningful. That's one way in which we're a mature field. In fact, I like to talk sometimes about computer science not having many lower bounds. They have a few, but they're not very good. And it's partly because it's a very hard problem to talk about what computation means, but it's mature fields that have them. And so optimization finally got some, and that's about 30 years ago or so. And once that happened, there was a flurry of work of saying, well, the existing algorithms actually don't reach these lower bounds. Could there be better algorithms, and what are their characteristics, and so on and so forth. So this is an ongoing in that, this work today is ongoing in that topic of finding how to explain, how to characterize the algorithms that achieve the lower bounds. So the lower bound arguments are sometimes like in statistics, they're kind of existence statements, and there's not really a generative mechanism for getting algorithms that achieve them, and that's what we're going to aim for today. I don't think I've mentioned my colleagues, maybe go back here for a second. Andre Wibisono and Ashia Wilson are students working with me at Berkeley, and then in the last little phase of this, Mike Betancourt, who some of you may know from MCMC work, has joined us. Okay, so let's just do a little math for a little while. So let's talk about unconstrained convex optimization. A lot of these ideas do apply to non-convex problems, but let's just be simple for today, convex. And it's going to be unconstrained, and we'll talk mostly about smooth optimization, but not strongly convex. So you all know, hopefully, an algorithm for working in this, when you have a smooth convex optimization problem, classical gradient descent. Okay, so the optimization literature uses x instead of theta, but translated in your own mind to theta for the purposes of this talk. I'm going to use x. So we want to know how fast this goes downhill. And that's already kind of an interesting problem. What do you mean? Because for any particular function, it goes at some speed, but it can be different for different functions. And so if it's a flat function, for example, you're at the minimum no matter where you start. So you have to talk about classes of function, and so it turns out in that class, unconstrained convex, that is the rate, 1 over k. Okay, so this is a nice little argument that kind of came out not that long ago. It's not an old argument. But anyway, it's a relatively easy argument to show that you get a rate 1 over k. We're allowing ourselves to set the step size beta in an optimal way. Okay, so now after having studied problems like this for a long time, you can compare them to conjugate gradient or whatever else and get rates for all those things. You could ask at some point, and someone did, what's the optimal rate you can achieve? Okay, so how do you formulate that? Well, you have to think of an oracle, the best algorithm, okay, that obeys certain rules. So what oracle are you going to use? It's not going to be something like Turing complete or something like that. It's going to be some limited computational oracle. And so the productive one that Nesterov found was to allow the oracle access to the function value and the gradient, and to allow each new point to be explored to be restrained to be in the linear span of all the previous gradients or subgradients. Okay, so you can't just willy-nilly explore everywhere. You can't be a super omniscient oracle, but you can do anything you want within the linear span of previous gradients or subgradients. Okay, so certainly gradient descent does that, conjugate gradient does that, and a lot of others. So it's an interesting question. So having done that, written that down, that oracle, then you can prove that the lower bound, you can prove a lower bound of 1 over k squared. So this is a very important result. It's faster than gradient descent. Okay, and that seems surprising because gradient descent is locally optimal, and if you're just looking in the span of all the gradients you've seen so far, it's not so clear how can you do better than that? Take the steepest descent direction. So it was an open problem, and then it was somewhat of a surprise when Nesterov discovered an algorithm which was faster, that achieves the lower bound of 1 over k squared. And in optimization, of course, it's very famous and well known, and outside of it, it's not that well known. It's surprisingly still hasn't gotten out there yet. It will. Anyway, it's 2 equations, not just 1, and one of them looks like gradient descent in the x variable for y, and then you take the last 2 y's and you take a convex combination of them. All right, so many people have studied or looked at those 2 equations and tried to figure out what they are. And they look like things you may be familiar with, but and so there's many attempts at explanations. I'd sort of say to this day, there's not been a compelling single explanation of where this arises from and then where it arises from in generality. When you look at non-Euclidean problems, when you look at extensions to higher order gradients and so on and so forth. I'm going to argue this is very close to something that some of you in the room will know very well, the leapfrog method. I'm going to argue that this is actually close to a form of symplectic integrator. Because there's a connection between these fields which has not been made before, which I think is there, and I'm going to try to make it at least almost fully in this talk. Now, I like to take dynamical perspectives on these things, look for Lyapunov functions and so on and so forth, and this one gives me pause, because this is kind of not very much, that doesn't look like dynamics, that looks like rotation, okay? And you have to wonder why a dynamical system would rotate at some point. How could that be good? But it does, and that's kind of the mystery that's going to come out here. Yeah?
How does this compare to conjugate gradient?
Conjugate gradient has the same overall rate, 1 over k. Yeah, it doesn't beat it.
No, I mean, this form looks also like a conjugate.
Yeah, well, so this form looks like a lot of things. I'm going to give you some examples on the next page. It looks like it's kind of doing take two nearby points. It looks like it's doing some heavy ball kind of thing. Momentum is often used to describe this, but it's none of the above. Okay, it's a little different. Okay, so that was in 1983, and so after that happened, that was a bit of a revolution. People, when looking at all the other gradient-based methods out there, things like mirror descent, cubic regularized Newton, and so on, all of which had known rates, and found the oracle rate and found there was a gap. And then were able to take the existing algorithm and accelerate it, a la Nesterov. And what that really meant was that Nesterov, you look at his paper, there was several pages of equations, and it was just some algebra that he was using in a certain way. And people kind of learned to use that algebra, and they applied it to other problems in the style of Nesterov. So I'd say this is just kind of algebraic manipulation, and people found other tricks for other problems. And at the end of it, however, there was a full literature on accelerated methods that you were able to accelerate almost all the methods. There was accelerated version of mirror descent, there was accelerated version of regularized Newton, and these things achieved the lower bounds, so they're important for theory. And in practice, especially when you're to composite problems, things like FISTA are widely used in practice. So this is very interesting. Now, there's a lot of mystery here. One of them is that these are not in general descent methods. Gradient descent is a descent method, goes downhill on every step. These methods will go downhill and they'll come back up. That seems odd. How could an optimal algorithm ever come back up? That just seems implausible, but it's true. And if you start thinking about Langevin and stuff like that, stuff that like kind of goes down, in some sense it has to be that those things are not optimal. So many people have tried to interpret these equations and similar equations that arise in other problems. Here's some of the recent papers that I really like. Chebyshev polynomials. If the underlying f function is a quadratic, then that pair of equations can be viewed as Chebyshev polynomials. So it's a very nice connection, but only quadratic case. And there's various other very nice ideas. These things are limited, though. They apply either to first-order problems or to Euclidean geometries or to quadratics. So there's not really been a general explanation. So I'm going to argue that the problem is that all of these are in discrete time. And they're trying to use kind of discrete time thinking without having an underlying dynamical system. And so if you're thinking about acceleration, you're thinking about somehow what's the best way I can optimize? How can I move quickly? And that kind of has to do with pushing your foot on the accelerator. And that's a notion that you can talk about in continuous time very easily. And in discrete time, it's just not as clear as what it means. So I think that's what the problem has been. So we're going to try to find a mechanism that generates the accelerated methods, and we will succeed at doing that. And then there's a lot of interesting complexities that come up. So it's not going to be, once we move into continuous time, it's not going to be that hard. And, then the whole problem is going to be getting back to discrete time. So the whole problem is going to be actually a numerical integration problem. And the fact that that's deep and non-trivial, if you're a physicist, you know this. So the whole area of symplectic integration arose because, oops, I heard a click up there. Oh, it came back. All right. The whole area of symplectic integration arose, leapfrog integration and stuff like that. That's not recent. That's the 1800s. That's Hamilton and Jacobi trying to do something very, very deep with the differential equations of physics. So that'll return later in the talk. It's maybe not surprisingly the hard part of this problem. It's actually the discretization. Okay, so let's go immediately in continuous time and start working there. So gradient descent, as you hopefully know, is a discretization of gradient flow, which is just a differential equation. There it is. Mirror descent is a discretization of so-called natural gradient flow. And it's what discretization? Well, it's most discretizations, but Euler method, for example. That gives you gradient descent. You can do either implicit or explicit, and you get different versions. Now, the mathematicians still to this day have books and analyze gradient flow. It's very interesting to them. There's a lot of research still going on gradient flow. And they can study rates and so on and so forth. Have a pretty rich vocabulary, talk about various symmetries, and so on. So you might think that it's worthwhile to take a continuous time look at the Nesterov equations. And so this was done in a very nice paper by Sue Boyd and Candace in 2014. They just took that pair of equations I showed you, took the step size to 0, and looked to see what differential equation results. And here's the one that results. So it's interesting. It's the second order. It's non-homogeneous. There's a funny term, mysterious 3 there. And there's the gradient. Okay, so first of all, it is second order. That's important. So we expect to get oscillations. And so we kind of expect to see things that go down and maybe come back up again. And so with this in hand, they were able to analyze this methodology a little bit more. You can't solve that equation, but you can use Bessel functions to approximate it. And they did that and learned a little bit about the oscillations and how they arise and so on. But it sort of ends there. It's just a differential equation. There's no reason why that differential equation arises. Why that differential equation? And what's the principle that led to that being the best differential equation? And how could you generate other such differential equations? Okay, so that's where we started getting interested in this. So with Andre and Ashia, we sat down for quite some time working on trying to find generative mechanisms for generating that differential equation and others, and see if we could find a way to do this in some general sense. And really this comes out from, it's a variational approach, it's Lagrange. So it's like taking some differential equations and saying, is there underlying integral expression that with calculus of variations would deliver these differential equations, because then maybe that object can be studied and it'll give us some insight. All right, so here I'm going to write down this page the answer. Okay, so here is the answer. This is something in an object we've now called the Bregman Lagrangian. That first term is critical. That's the Bregman divergence. Let me show you what that is first. So the dH there is the Bregman divergence based on the auxiliary function h. So hopefully you've seen Bregman divergence. It's a way to measure distance in a arbitrary metric space between a point x and point y. What you do is you put down an auxiliary function h. You take the linear approximation to h at x, and you take the discrepancy between that and h at y, and that vertical distance, red distance there, measures the distance between x and y on the x-axis. So if h is just a quadratic, this is just another way to write Euclidean distance. It's a variational way to write Euclidean distance. But if h is, for example, logarithm, then you get Goldbach-Lieber divergences, and you can get lots of other kind of interesting divergences in this way. All right, so we're using that in an interesting way. It's the first term in this Lagrangian, and it measures the Bregman divergence between x, where you are now, and x plus a time scaling, e to the minus alpha t. So that's just, the e is being used for convenience. It's just a time scaling, times x dot. So it's kind of looking a little bit in the x dot direction and measuring the Bregman divergence. So it's a little bit like an elasticity or an energy in that direction, okay? Measured in this particular way. Now, all these alphas, betas, and gammas are just degrees of freedom we give ourselves to give us a space of algorithms, not just a single algorithm, okay? So they're not that important. They're just time scalings that give you different algorithms. The important part is that Bregman divergence, and then minus f of t, or f of x, sorry. All right, so we're calling this a Lagrangian because it looks kind of Lagrangian-like, but in particular, if you make h the quadratic, just look at that special case, then this reduces to 1/2 x dot squared, so it's a kinetic energy. All right, so this looks exactly like it is a kinetic energy minus a potential energy, and the potential involves the function to be optimized, so that looks pretty physicsy. Okay, but in general, we're not only interested in Euclidean problems and Euclidean geometries, and we like logarithms and so on, so we'll call this a Bregman Lagrangian to be more general. So what do you do with Lagrangians? Well, you put them in the calculus of variations and you see what differential equations drop out. So before we do that, just to mention that although there are 3 degrees of freedom up here, to obtain the optimal rates out of this formalism and not just algorithms, it turns out that there's really only 1 degree of freedom. So if you set alpha of t, that's going to determine beta of t and gamma of t, and so any one of the 3 of them determine the other 2, so that's really just 1 degree of freedom. Okay, so let's do calculus of variation. So at the top, I've just written down again this Bregman Lagrangian. Remember what you do with calculus variations. You stick a Lagrangian inside an integral, and you optimize over paths x. Find the path that minimizes this single number. And there is a necessary and sometimes sufficient condition for optimizing that problem. It's called the Euler-Lagrange equation, which is just a differential equation. You know, it has partial derivatives in it. You just hit that Lagrangian with some partial derivatives with respect to x and x dot, and then take a time derivative, and out will pop a differential equation that characterizes the optimal path. That you can obtain the optimal path by solving that differential equation if you wish. So here is that differential equation. This is going to be our master differential equation. It's just gotten by taking that thing and doing the 3 lines of calculus to get this. So it turns out to be second order. It is non-homogeneous in this particular way. And then there's some geometry here. And then there's this gradient of the function to optimize. All right, so I claim that this equation, this master equation, generates many, if not most, of the known acceleration algorithms, including mirror descent ones and cubic regularized Newton and so on and so forth. But even more importantly, it allows you to get some more mathematical understanding of all of these objects. Okay, so the first thing we're going to do is look at convergence rates. So this differential equation converges, all right, and it converges at a certain rate. Now normally the convergence proofs for these kind of, all these different algorithms out of the Nesterov school are all special cases that you have to work on them separately, and there are 2 or 3 pages of equations to get the convergence rate. I'm going to show you that for this entire family we get the convergence rate in a one-line proof. So that already shows us that we're somehow on the right track. So here is the convergence rate. It is O of e to the minus beta t. So that beta that we get to set as a degree of freedom determines the convergence rate. So we get to sort of pick the convergence rate we want. Right? And the proof is just, it's very simple. You write down a Lyapunov function. So here's a Lyapunov function for this problem. It involves the Bregman divergence in a slightly dual way. And then you take a Lyapunov function, you take its first derivative, and you set that to be less than or equal to 0. That then gives you, you have that if and only if you have convergence. And that condition is achieved by the convergence rate shown above. So it's a one-line proof for convergence in all these situations. All right, so that's interesting, but the result is odd because it says that we can achieve exponential rates for these problems. And that was, that's odd because we know that the rates we were kind of expecting to see were 1 over t, maybe 1 over t squared, to meet lower bounds. We're now in continuous time, it's not k anymore, 1 over k squared. And also if we had stochastic diffusion-like things, it might be 1 over square root of t, and so on. We expect those kind of more polynomial-like kind of rates, not these exponential rates. All right, if we had like strong convexity, we might expect these rates, but not otherwise. All right, so what's happening? Well, first of all, what's happening is that we can actually achieve exponential rates in continuous time. Okay, and in fact, it's not a big deal. It's you can just turn up you can change the definition of the clock, how you measure time, and you're free to do that in continuous time. You're not free in discrete time. The other thing, though, is what's going to happen is that as soon as you turn up that rate to be too fast, if you're too ambitious in continuous time, you will no longer be able to discretize and get a stable set of difference equations. Something will break at that point, and that's what becomes mathematically interesting. Okay, so let's start to understand that a little bit. First of all, by just being not ambitious, saying, we realize we don't expect rates in the form e to the minus beta t, so let's let beta be logarithm of t to kill off that exponential. All right, and let's put a degree of freedom there. Let's call it p log t. Then we will get rates of the form 1 over t to the squared, and maybe 1 over t cubed. Maybe we get all the polynomial rates out of this methodology. Okay, in that sense, we'd be discovering some actual new algorithms. So in fact, let's do that right here. Beta t, let's set that to p log t plus a constant, and then that determines, as I mentioned before, alpha and gamma. So when you do this non-ambitious thing, you do plug in for the rate, you get 1 over t to the p, which could be 1, p could be 1, or p could be 2, and so on, to get the things that we expect. And now the master differential equation looks like that. So it starts to look a little simpler, the geometries become a little more apparent, and that leading non-homogeneous term is now p plus 1 over 2, or over t. So if you set p equal to 2, and you set h to be the quadratic, a lot of cancellation happens, and you get the Boyden-Candes equation. Okay, so we've recovered that. You also, when you set p equals 2 and you set h not to be quadratic, you get out the corresponding equation for mirror descent, which was also studied. There was a differential equation for mirror descent studied by Krichin et al., where they got the 1 over t squared convergence rate with a certain differential equation, which is a special case of this as well. Okay, so that's kind of interesting. We're on the right track. Let's see, though, if there's something that makes this family kind of cohere together, or all these kind of separate problems. So let's write down the differential equation for p equals 2, 3, and see what happens. So there's the differential equation for p equals 2. Here's the one for p equals 3. And you don't have to be knowledgeable on differential equations to sort of see these are pretty similar equations. So that the 3 became a 4, the 4 became a 9, the 2 became a 3. Otherwise, it's exactly the same equation. Okay? So that says that the problem where we've set p equal to 2 or p equal to 3 is really the same problem in some sense. All right, and so what's exactly happening here is that this operator, this Lagrangian, is a covariant operator in differential geometry language. So as you change p to different values, p equals 2, 3, 4, whatever you want, you actually go through exactly the same path in phase space. Okay, so in that sense, there is an optimal way to optimize, and that path given by that Lagrangian characterizes the optimal way to optimize. So it's not actually about the speed per se, it's about the path that you go along. Right? And so all these algorithms follow the same path, and they only differ by changing the clock, the notion of the clock. So it's just like Einstein, it's relative. So if Gareth likes, his time is t, and I set time to be t equal to the 3/2, my clock's just different, I'm free to do that. I get out the same path, and I just move along it faster. Okay, so in continuous time, acceleration becomes not interesting. It's kind of, it's simple. Okay? All right, and the proof of this is just a substitution. So here we've literally taken t up there and set t to 3/2, and then just done the appropriate calculus, and we get out this equation. All right, and the general proof that this is covariant is that you substitute in, and you get out a new version of the parameters for different values of p. And by the way, gradient methods do not have this property. So if you go from gradient flow to scale gradient flow, replacing the square here with a p, you do not follow the same path. So we had to go to these second order equations, these momentum methods, to sort of seal this mathematical structure. Oh, and there is the proof right there that this is a covariant operator. Okay, so we've learned something. We've learned that we have a single path to follow for a range of accelerated problems, and we learned that acceleration is not interesting in continuous time, but it is interesting in discrete time, and if we try to be too ambitious, something must be breaking. So what's going to be breaking is how to discretize. And so at some point, if you're going too fast, if I use a clock that makes me go at exponential rate, then I'm not going to be able to get back into discrete time. I can't put this on the computer. All right. So let's try to do it. Let's take our second order equation. And by the way, at this point it starts to get, there's going to be lots of symbols that I don't want to really dig into all the details. It's just discretization of differential equations, and so symbols start to arise. But you'll get the message without focusing on all these little symbols, okay? If you're used to this stuff, it'll be straightforward, but you know, the details don't matter so much here. They're in the papers. So how do you take a second order differential equation and you discretize it? Well, you turn it into two first order equations and you discretize those. So we've done that here. Here's two first order equations, and we discretize them with Euler's method, and pop out two difference equations. And so we've written it kind of in a Prox method way, and there's your first order one. So it looks a little bit Nesterov-like, you know, but it's different. It's not Nesterov. All right, and in fact, when you try to implement this thing, and Andre did that, and he showed the following, that it does converge down towards the optimum, and then it hovers around there for a little while, then it shoots off to infinity. So it's actually unstable. And you would not want to propose anyone using this, okay, because you don't know when the stability is going to hit. And here it is in one dimension. You see the instability. Okay. So we thought, okay, we know something about differential equations. Let's go to Runge-Kutta, higher order. Let's go to stiff differential equations. Let's go to that literature. And at some point realize that none of them are going to work. That this thing is not going to it's not going to be discretized just so easily. All right. So this is about a year ago, and so still kind of we were figuring, can you discretize these things at all? All right. And at that point, we went back to the Nesterov paper and looked at his equations again. There is some magic there, but thought about those equations now not as coming out of Nesterov's brain, but thought about as discretization methodology, maybe a new one for differential equations, for a certain class of differential equations. All right, and thinking about them that way, we got a method. And so I'm going to show you that method. It does work. And here it is. And if you don't know about Nesterov's kind of work, now this will be a bit of a mystery, but this is this is not the important part of the talk. What we've done now, it's kind of a variable augmentation trick. We've taken those original two equations that had just an x and a z, and we replaced the z with a y on the right-hand side in two places. So there's a new value, y, and now we're going to get three equations, x, y, and z. And if y satisfies a certain sufficient condition right here, that an inner product with the gradient of f at y is lower bounded by the gradient in a dual norm. So if you work with optimization, this is actually not so mysterious, and you know how to achieve this. If that sufficient condition holds true, then our three set of equations are actually provably stable, and they provably achieve the fast rate. So this is gotten by, again, kind of reverse engineering Nesterov. So here's the theorem. That is stable, it converges, and you achieve the 1 over k to the p, not p minus 1 would be the slow rate. Okay? So this proof of this theorem was done by just going back to Nesterov's techniques. He has a technique methodology called estimate sequence techniques, and just doing that. And more recently, in a paper, Ashia Wilson has followed this up and developed a Lyapunov approach for the discrete time sequences as well. So you can kind of bypass the Nesterov technique altogether. You can take the Lyapunov function in continuous time and turn it into a Lyapunov function in discrete time mechanically, and then get these rates. So, it's all right?
P is less than 2.
I can't hear you.
P should be less than 2.
P is less than 2.
No, P is not less than 2. No. No. No, definitely not. All right, so there is the resulting set of three equations. Again, I don't really care that you pay too much attention to this, but anyway, when p is 2, we get the accelerated gradient mater descent. When p is equal to 3, we get our known algorithm called accelerated cubic regularized Newton's method. And when p is bigger than 3, 4, and so on, you get a new family of algorithms. Now, it turned out there was a paper, unpublished paper by someone named Michel Baïs, who had already discovered these algorithms independently, but this is a different way of arriving at that class of algorithms. Okay, just to summarize what we've done so far, and then I'm going to do this a little bit on symplectic integrators, is that the literature has studied these gradient methods for quite some time. The gradient, the Hessian versions, and higher order methods, all in discrete time. There is a mathematical literature that also does it in continuous time, and it's not all that used, and it's partly because it doesn't have that many beautiful mathematical properties. It doesn't have covariance. So it's just a different way of expressing some of these ideas than a formalism that some people find more familiar. Nesterov, in this brilliant set of papers, took us over to this right-hand side here and showed us how to accelerate all these methods in discrete time, getting algorithms that go at rates 1 over k to the p, not p minus 1. And so what this paper has done is shown us there's a corresponding continuous time interpretation which is best expressed variationally with a Lagrangian, and that gives you rates, provable rates of 1 over t to the p, and partnering with all of the higher order methods in discrete time. Okay, so that was about a year ago. We have a published paper on this, but we were still unsatisfied about this discretization. We just didn't feel like we'd understood it in any real way. And so I vaguely at some point remember that I'd taken a class back when I was a young assistant professor at MIT on differential geometry. I learned about symplectic integrators and just stored it away. And how many of you know about, this is a sophisticated audience, how many of you already know about symplectic integrators? Yeah. Okay, the handful of people I knew about it, but yeah, it's funny because it's a period, the leapfrog integrator is a symplectic integrator. So if you know about that, you somehow know about it. But it just kind of was brought back, and maybe Gareth or someone else can tell me who did that, but maybe Radford or somebody just brought it out of that literature, plumped it in the middle of HMC, and then added some machinery around it so that it became not only a good algorithm, but apparently a very, very good algorithm. But I don't think anyone's kind of thought too much about why that leapfrog integrator is so important in there. And are there other things you could pop in there, and what's the general story? And so I'm not going to be able to answer all those things, but I am going to sort of claim that, there's now going to be a new connection between MCMC and optimization that arises because of symplectic integrator. I think that's opening up. We have not resolved all the issues here. I'll show you very clearly what we have not resolved. So I want to invite people here to jump in and start to work on this as well. I think it's going to be pretty interesting. So let me just say a little bit about that. So first of all, last little statement here. This is just summary of everything. This is now going to be important, which is that if you're a physicist, you know that you can write things in terms of Lagrangians. You often can write them also in terms of Hamiltonians. And the way to get from a Lagrangian to Hamiltonian is take a Legendre transform. So instead of having variables x and x dot, you do a Legendre transform on the x dot, and you get a variable that's often called the momentum. Let's just call it p. And you take a pair of variables x and p, and you re-express your Lagrangian. That becomes known as a Hamiltonian. And Hamilton, of course, derived this and showed that it had other mathematical properties that just plain old Lagrangians don't have, and so there are some advantages associated with it. Okay, so around that time, they also, for some reason, Hamilton, Jacobi, Betancourt, and others were interested in discretizing the class of differential equations that came out from Hamiltonians. And I don't actually know all the history of why they were interested. They didn't have computers yet, but nonetheless, they were interested in discretizing these differential equations. And they asked the following very interesting question. If these Hamiltonians describe underlying physics, there will be some very important quantities that they conserve as you flow along the vector field. So energy, momentum, and then the whole differential geometry machinery got used to show there are certain exterior forms that are conserved, and that characterizes the class of things that are conserved. And many of these things are not just energy, momentum, there are other things in physics that you care to conserve. And when people started discovering that, they started discovering other physics that came out from wanted to conserve other kind of things that from this approach. So the Hamiltonian was deriving all those things, and it was of interest then to say, well, can you take the Hamiltonian and get out a discrete methodology? Can you discretize those differential equations and still exactly conserve momentum or energy or other exterior forms? All right, so why? Well, if you're simulating the cosmos or a protein and you write down the differential equations, you start simulating on a computer, of course you're going to, the underlying curves you'll be approximating, but if you're bleeding away energy or momentum, just after a while you're not doing the physics anymore. Okay, it's just wrong. And so they realized that that's just a bad idea, and they asked mathematically, can you do the physics? Can you do it approximately, but exactly conserve energy or momentum. Okay, so that's a math problem, and they solved it. All right, and so the way they, there's a whole textbooks on this. It's a beautiful, beautiful field. And just a little intuition about what they did is that they said, well, instead of just taking the vector field point of view, you're at a certain point, you look at the vector there, maybe you look at the past vector and the next vector or something. Instead of just doing that kind of locally, what you do instead, you look at a triple of vectors sitting there right there. And that triple of vectors has a determinant and a certain volume. All right, and so what you want to ask is that as you flow that little piece of volume element along, you want that volume to be exactly conserved. All right, and that gets you some equations now for all three of those members of the triple and for the determinant. And the determinant gives you some pluses and minuses, and that leads to all the implicit, explicit integrator kind of stuff that you maybe know from leapfrog methodology. Okay, but it really has to do with kind of a stiffness of volume elements around this flow. All right, now here we're not necessarily know what we're trying to conserve. I think that's going to actually be interesting to figure that out. But what's the extra added fact about this is that once you wrote down these integrators, they turned out to be able to be ones that allow you to move much, much more fast through the space. And that's another fact. I didn't really, it's another explanation is needed, but kind of in some sense intuitively, the stiffness is what's working for you. That you're preserving volumes, and that means you don't flow away too badly. All right. So anyway, long story short, you can move like an order of magnitude farther than you can with competing methods. So quite amazing. Generally, just kind of syntactically, if you write these things down, these integrators that satisfy these conditions, they are a blend of an explicit method and an implicit method. So just like in a leapfrog, it's exactly one implicit equation and one implicit equation. That's kind of the character that they have syntactically, but the deep understanding comes from this perspective, this differential geometry perspective. Okay, so with that as background, we spent the fall reading on symplectic integrators, and I'd given a talk about this, and I mentioned this, we were working on this, and then Mike Betancourt came up afterwards and said, hey, I know something about symplectic integrators, and so I invited him to Berkeley, and we started talking, and we now have a new paper we're just finishing this week that tells the following story. Oops, this is not exactly the slides I wanted. All right, well, I'm nearly done anyway. I'm just going to show you a couple of pictures. So I've just sort of said this, that symplectic integration is this whole field. One small issue here is that our Hamiltonian, if you'll remember it from earlier, is time varying. So most of the Hamiltonians you're used to in physics are not time varying. But you can add a time variable explicitly and its conjugate variable, energy, and let's call it an energy. And the overall Hamiltonian is now time varying, and you can apply these techniques to that. So we did that. It's not the exact slide I wanted, but as I alluded to, if you take the symplectic approach, you're able to take much longer steps. So if I take a certain step size, like 0.05, and I use that to discretize the Lagrangian, I will maybe go unstable. But for that same exact step size, if I symplectically discretize the Hamiltonian, I'm stable. And I can turn up the knob much, much higher for the symplectic integrator. And so you sort of see some stability issues here. So if we're trying to go as quickly as possible, obviously you want to have a large step size. And this technology allows us to have large step sizes. And so here is symplectic integration of the Bregman Hamiltonian, just doing it out of the box, okay, with a particular symplectic integrator. You can see the oscillations, and that slope is exactly the theoretically predicted rate from this oracle theory. Okay, so we didn't have to do any more thinking, no more reverse engineering, no more hacking. This just applies and works. Okay, so to that extent, once we started to see this, we thought, well, we've solved the problem. We now know what Nesterov acceleration is. It's actually not quite symplectic integration, but it's a more hacky version. Here's the right, pure way to do it. Okay. Right, then we plotted Nesterov acceleration on these same, this is just a particular function, okay, it just happened to achieve that worst case rate. But we plotted Nesterov acceleration there too, and of course it comes down and it has the same rate for a while, but then it actually does better at the end than this symplectic integrator. Why? Well, kind of what's happening here is that these integration technologies are set up to do far away from the optimum. They move you really fast in with momentum. When you get really close in, you don't want to have all this momentum sloshing you back and forth. You want to converge. Now in MCMC, you don't want to converge. So, maybe it's not an issue there. But here it's an issue. So what Nesterov is effectively doing, it turns out, is kind of turning off the momentum and turning on gradient ascent at the end. It's implicit, but that's what's actually kind of happening. So last little story here is if we just add in gradient flow, now we're being ad hoc. This is not principled. We just add in gradient flow to our previous equations, discretize both of them simultaneously. We just have a mixed flow, All right, now we get out here a better result. Here's our dynamics only, and here's our mix. It has the oracle rate for a while, and then it actually does better near the optimum. And if you then compare it, right, here's my last slide, right on top of Nesterov, it's just exactly as good as Nesterov. So it's a little more principled. It has this nice symplectic approach. It's just as good. It's the state of the art. There's nothing that beats it we know of. All right, and moreover, this is an old slide. The new ones that we have in the paper that's coming out this week have results that show we can get the whole symplectic mix to slide over by a factor of about 10. So it's actually now beating Nesterov quite substantially in the early game, and then they're doing very similar near the end. Okay, so I'm going to just stop there because I've run out of time, but I hope you get a little bit of the picture here. I think this is an emerging topic. This was all done with discrete and continuous differential equations. There was no stochastics, no diffusions. Obviously worth working on. We are starting to do that on doing this for diffusions. There's also doing this whole thing on manifolds, very interesting thing to be doing. And I'll stop there for questions, but I hope you can see this is just getting going. This is definitely not the end of the story.
So, in my understanding, this is all applied to convex functions. But if you
All applied to convex?
convex functions,
Yeah.
But what if you have some highly non-convex function, like a neural network, for example?
Yeah, so I'm working a lot on those kind of non-convex things in a separate talk. I could talk about it. And the main interesting problem there is really saddle point avoidance. Because these neural nets especially, they all have, you can get to zero error. In fact, there's kind of a theory now that suggests if the network is sufficiently wide, from any starting place, there's a downhill path to a global optimum. So people think of these as really hard problems to optimize. I don't think they are. So what's interesting then is that, so there's some global optimum you're going to reach, and we don't know which is there's many global optimum, which is a good one statistically is a whole other issue, but just from the opposition point of view, there's one you're going to reach, and around that global optimum there's going to be some saddle points, and then probably there's several rings of saddle points. And so the whole question is that if you start out here somewhere, you're going to go past the saddle point. How long does it take you to get past the saddle point? If that takes you a long time, then you're going to converge slowly. And you may not even know that if you flattened out, you may not know that the game is not over yet. You could get a better result. And moreover, how does that go as a function of dimension? If in 2 or 3, if it was going up in dimension, your relaxation time past the saddle point, that would be no good. So we have a paper that's just come out this past few months that shows that stochastic gradient or a perturbative gradient avoids saddle points, and it has exactly the same rate as stochastic gradient up to a term which is polylogarithmic in dimension, log to the 4th. So it's basically just as fast as stochastic gradient. All right, so we're putting that together with this variational characterization here, going to continuous time and re-expressing the ideas there. So that's the attempt to sort of see. My intuition, and I don't know, maybe again some experts in the audience, maybe Eric would know, just momentum on itself should kind of help you to get past saddle points, but I don't know of actually any result that says the rate of acceleration is still preserved when you go to non-convex saddle point situation. So that's an interesting question as well.
Okay.
Yeah, non-convex really, the main thing is just saddle points, and there's an emerging theory about that. I mean, there are other issues, and as you go further and further, global optima and stuff. But I think that's the current issue that's worth studying.
Okay. Can we thank the speaker again?